So this is a joint work with Davide Barbarossa, and this talk is about formal methods. And there are several reasons to consider formal methods for software analysis. For instance, we want to ensure that the program is correct. Sometimes we want to ensure that it's terminating or control its input-output flow. But from a more theoretical perspective, the challenge is really to understand the notion of computation itself. And to do so, we represent a program as a more abstract structure so that we can use ideas and principles from mathematics to the study of programming languages. And the problem is that today's software is very complex. In general, a program can be very long and complicated. So we need to develop a theory of program approximation so that we can slice our program into elementary bricks that we call its approximant. And then we retrieve the whole program by performing some kind of limit of such approximants. So the theory of program approximation has been first developed in the framework of pure untyped lambda calculus. And the idea was to use continuous semantics. So the continuity in this case means that a finite portion of the output of a program can only be generated by a finite portion of its input. And using continuity, we can model the recursion as by computing least fixed points. And this allows Scott to define the first model of lambda calculus, the infinity. Some years later, Barendrecht proposed a more syntactic model based on bum trees. And the idea was to associate to a program a possibly infinite tree representing its execution. But the definition of a bum tree is not inductive, it's co-inductive. And so, if you lived in the 70s, that was scary. And for this reason, the researchers used an approximation theorem, stating that if you have a bum tree, then you can see it as the supremum of all its finite approximants. And this is very nice and works smoothly for the lambda calculus, but it is difficult to generalize to mainstream programming languages, like the algebraic, differential, probabilistic, and quantum calculi that are of growing interest in this community. So what all these languages have in common is that they can be naturally interpreted in models arising from linear logics and based on vector spaces. And while studying these models, Erard and Renier realized that the notion of differentiation was at hand. And this is nice, because in mathematics, derivative allows to compute the best linear approximation of a function. So actually, we study the derivative to get information of the original function. So the question is, can we do the same for programming languages? And the answer is yes, if we understand what does it mean, the derivative in this context, from the point of view of computer science. So the derivative of a program is a linear program. Linear in the sense that it uses its argument exactly once. It cannot neither erase it nor duplicate it. And then, if we have a syntactic derivative operator, we can, for instance, import the Taylor formula from mathematics to computer science. And we can expand a program as a possibly infinite series of purely differential programs. So the ambitious goal here is to replace the old theory of program approximation, which was based on continuity and bum trees, with this newer theory of approximation based on resource consumption and Taylor expansion. Nowadays, the target language of the Taylor expansion is presented as a resource calculus, whose terms have more or less the same syntax as lambda terms, except for one case, the application. You cannot apply a term to another term. You need to apply to a bag. What's a bag? A bag is a multiset of terms, and each of these terms is available exactly once for the program. To be more precise, if we have a program like this that computes a value, This means that each of these Si has been used exactly once in the reduction. And what happens if the program tries to erase or duplicate one of its arguments? Well, in this case, let's say that it raises an error, a 0, and the whole program self-destructs and becomes an empty program that we call 0. So I don't expect that you get familiar with this calculus now, but what I ask you is to remember its properties. It is strongly normalizable, and this is trivial to check because there is no duplication that is involved. It's confluent because it is locally confluent and terminating. And then it's linear, and this means that nothing gets erased or duplicated during the reduction. So now we define the Taylor expansion of a lambda term that transforms a term into a set of these resource terms. And the only interesting case is the application. So the Taylor approximant of M applied to N also have the shape of an application where T is a Taylor approximant of M, S1, Sk are Taylor approximant of N, but how many they are? Well, in principle, a priori, we do not know how many times T is going to use its argument, and so we consider all possibilities. So you see that this is an inductive definition, so all Taylor approximants will have more or less the same shape as the program that they are approximating. So this definition is static, but we can endow it with dynamic semantics. How do we do that? Well, our calculus is strongly normalizable. So the normal form of the Taylor expansion is just computed by taking the normal form of all the elements in this set. So now we have two ways of approximating a lambda term. We can either compute its Bern tree, like this, or first we do the Taylor expansion, and then we compute its normal form. What is the advantage of using the Taylor expansion? Well, that here approximants are closed under application, which is not the case for Bern tree approximants. Moreover, we have strong normalization, confluence, and linearity. And this approach with the Taylor expansion do generalize to the mainstream languages. There are, of course, also inconveniences. Since this language is linear, a lot of indices arise from the linearization. So these two walls, how do they compare? Well, Erard and Regnier showed that if you first do the Bern tree and then the Taylor expansion, is the same thing as first doing the Taylor expansion and then normalizing. So if you look in the literature, in the recent literature, you can see that researchers have generalized this notion to, for instance, call-by-value lambda calculi, probabilistic lambda calculi, algebraic lambda calculi, and so on. And usually, they prove some kind of generalization of this commutation theorem by Erard and Regnier. What we find a bit disappointing is that they do not use this theorem to prove properties of programs. And this should be possible, because as a corollary of this, you get that two programs are equal in the Bern tree semantics, if and only if they are equal in the Taylor semantics. So what we did in this paper is try to explore the real power of the Taylor expansion. How to do this? Well, we consider the most fundamental results in lambda calculus, like contextuality of Bern trees and the genericity lemma, that are consequences of Scott's continuity. They are proved via topological argument. And then we also looked at the perpendicular lines lemma, which is proved using Kahn and Plotkin sequentiality, and that entails the non-existent, the non-lambda definability of parallel OR. And so we have seen that using this commutation theorem, we were able to reprove the contextuality of Bern trees and the genericity lemma. And a posteriori, this was not surprising, because we can actually prove Scott continuity. What surprised us more is how simple these proofs are. And also that we were able to prove Berry stability and the perpendicular lines lemma as well. And this means that this commutation theorem is more powerful than Scott continuity. In some sense, it subsumes continuity, stability, and sequentiality. That's the title of the talk. So now I've said that these proofs are simple. So I need to show you at least one example, not the whole proof, but at least the structure. And I chose a statement, the contextuality of BEM trees. We have to prove that if two programs have the same BEM tree, then whenever we plug them in a context, the new programs that we create also have the same BEM trees. This is a fundamental property of BEM trees. So using the commutation theorem, we can rephrase this as an equivalent statement that only speaks about Taylor approximant of these terms and its normal form. And we can prove this by structural induction on the context. And this, if you know the original proof, it's amazing. So the idea that we use is that whenever you take a Taylor approximant of this context, since this context is an application, because application is the only difficult case, that's why we are considering it. So if we take something in this set, then it must have the same shape as the original term. So it must be an application. An application of what? Of something that comes from M, and also the U1 UK comes from C2 of M. Okay, so using confluence and strong normalization, we are able to single out a single reduction to the value. And this is the reduction we need to be able to apply the induction hypothesis. So we apply the induction hypothesis and we conclude the proof. And this kind of techniques, so confluence, strong normalization, linearity, plus induction hypothesis, are used in almost all the proofs that you will find in the paper. So I don't have time now to give you all the details of all the proofs. Just I want to conclude this talk by looking at the perpendicular lines lemma, because it's a particularly nice and interesting statement. The statement says that if you take a context, an n-ary context, so that takes n lambda terms and gives a lambda term, if this is constant on n perpendicular lines, then it must be constant everywhere. So what does it mean in lambda calculus to have n perpendicular lines? Well, the idea is that a line in lambda calculus is analogous to a line in the Euclidean space. So the idea is that you just take the tuples and you have fixed all components but one. So these are lines in lambda calculus. So here we fix the first and the second and the third. And two lines are perpendicular if the component that you move is different. Okay, so known results are that the perpendicular lines lemma holds if you consider the BEM tree semantics. And this is proved by sequentiality. But it also holds if you consider beta equality. And this was proved by De Vrije and Androulis via the reduction under substitution property. But Barnes and Statman showed that if you only consider closed lambda terms, in this case, there is a counterexample based on Plotkin terms. And so this is not true for the closed term model of lambda beta. And the question is, does it hold for the BEM trees when you consider only closed terms? We don't know. So the statement is like this. If you have a context that is a constant on each of its coordinates independently, then it must be uniformly constant on all coordinates. So here we are in the theory of BEM trees. So we need to understand why a context can be constant. And there are several reasons. Either the trivial one, so it does not contain the whole in the first place. Okay, that was easy. Or because the whole is erased during the execution. Or because the whole is hidden behind a looping subterm, so the BEM tree doesn't see it. or because the whole is never erased, is always there, but it never goes in head position of a subterm. So you don't see it in the Bone tree. But now, thanks to the commutation theorem, we can retranslate the whole statement just by using the equality arising from the Taylor expansion approximation. So now, if you take a Taylor approximant in this context that does not go to 0, because otherwise it's trivial, then it can be constant for only one reason. Why? Because the whole cannot be erased during reduction, because their calculus is linear. It cannot be hidden behind a looping subterm, because there are no looping subterm. It's strongly normalizable. And it can never be pushed to infinity because it's a finite calculus. It cannot go to infinity. So we are left with one reason, the trivial one. And then you can state a claim which is very easy. If you have a context that does satisfy the hypothesis of the statement, then whenever you take a Taylor approximant in its Taylor expansion, if it doesn't go to 0, it's because it doesn't contain the whole at all. And so from this, you can easily prove the statement. And our proof, we realized, doesn't use at all the fact that these terms are open. And so also holds for the closed term model of Bone trees. And this allows you to put a tick also in the last square. Okay, so what should you take away? Well, that this paper is not meant to be about untyped lambda calculus. Okay, this paper is about Taylor expansion and reverse approximant. And what we wanted was to raise the awareness in this community that these techniques are available and you can prove nice results with it, both quantitative and qualitative, like we did this. And we chose as a framework the simplest one, the untyped lambda calculus. But this technique should generalize to all mainstream languages. And this concludes my talk. Thank you very much.
We have time for a few questions from the audience.
So you mentioned that linearization can cause an explosion of indices. Where does that happen? And clearly if you have like a binary branching like pairs of linear things, you'll get like exponential blowup, but like have you found ways to mitigate that, or where do you see that happening the most?
In the proofs. So the fact is that I didn't show you the rule for reduction in the resource calculus. But the point is you have your term with, say, 100 occurrences of the variable x. And you apply it to a bag, so a multiset of 100 different values. And then in the reduction, each of these resources goes in one particular occurrence of that variable. Okay, and since there is no canonical way of associating the arguments and the occurrences of the variable, you need to consider all possible choices. So you are, in the reduction, you are doing big sums. And this was hidden in the talk because I had 70 minutes. So it's from this fact that every time that you reduce, you have this association that there are more and more indices appearing. Well, on the, let's say, if you want to implement, in some sense, the Taylor expansion, you need to, on the one side, truncate. So take, for instance, a number n, and say every time I take an approximant in the Taylor expansion, I just allow myself to take at most n copies of my argument. And now you have to cross your finger and hope that at least this gives a finite result. So that could be a way of bounding this.
Thank you.
We have time for one more question. Okay, in that case, let's thank the speaker.
Thank you.